In the last lecture, we talked about the classical Dilogarithm function. So we have several versions, the Euler's origin definition, we have the Rogers version, and also the Bloch-Wigner function. We discussed its properties. One of the most important one is the pentagon identities. So this is the functional equation involving 5 terms. And later, we use the cluster algebra language to describe a generalization of these pentagon identities into a more general version using the tropical mutation of the Y seed. And we see that the pentagon identity precisely corresponds to the quiver with 2 vertices, 1, 2, and the mutation sequence 1, 2, 1, 2, 1. Right, so this is the standard type A2 cluster algebra that we have encountered many times throughout the whole lecture series. So today we will talk about its generalization called the quantum dilogarithm, and we will see that in fact the pentagon identities of the classical dilogarithm will be generalized to the quantum case, and this function is very old. It's known as the double gamma function by Barnes, introduced in the 1900s, but it is kind of useless until very recently by reintroduced by Faddeev in the study of integrable systems in say 1990s. So this function later turns out to be very useful, in particular to the cluster varieties introduced by fock-goncharov, where they show that the mutations formula involved actually can be written very explicitly in terms of the conjugation of these quantum dilogarithm functions. And then in the real case, where all these operators becomes operators on a Hilbert space, then this quantum dilogarithm will provide us intertwiners of the Hilbert space. So they will be unitary transformations, and they provide unitary equivalence of different representations of the quantum cluster algebra. So for the quantum dilogarithm, we have basically 2 versions. One is the compact version, where everything can be written in terms of a power series. And the other is the non-compact version, where the power series fails to converge, but somehow you can modify them so that it becomes actually a meromorphic function on the complex plane. And this is then used to define all the operators on a Hilbert space, on a Hilbert space. All right, so let's first start with the very basic definition. So our function will be denoted by psi q of x, and we will let, first of all, that q is a parameter where the size is a complex parameter where the modulus is less than 1. And we let x to be the argument, where to avoid stupid division by 0, we will say x does not equal q to the minus 2k plus 1 for integer k, or actually for positive integer case, say. Then this function is defined to be 1 over the Pochheimer symbol. This. So for notation, bracket A semicolon Q bottom n is the product of n terms. So this is known as the Q Pochheimer symbol. And then for the infinity version, you basically just take limit of n goes to infinity. So it will be an infinite product. But then formally, you can also write it in terms of a power series, right? So if you expand the 1 over Pochheimer symbols into a power series, then it has an explicit formula given by the following. So one important point to note is that this power series actually does not have an infinite radius of convergence. So the radius of convergence is actually finite. In any case, so this is one way to write down the quantum logarithm functions. And we will explain later why it is called quantum logarithm. But actually, another very closely related function is the quantum exponential function. So the quantum exponential function is written, let's say, EQX. So as a power series, it looks very much like the exponential function, but instead of n factorial, you have the quantum number n factorials, where the quantum number is defined by the following. So as you can say here, it is a quantum version of the number n, because when you take the limit when q goes to 1, then this number basically just goes to n. So it's like a q deformation of the number n, and then the factorials is just the standard one where you multiply the quantum number from 1 to n. So this is the n factorial. So you can see immediately that this is the q deformation of the usual exponential function. But instead of n factorial, you introduce the q n factorials. So if we use this notation, then we can easily see that our quantum Dilogarithm function actually is nothing but the quantum exponential function with appropriate parameters. Right, so why it is called quantum Dilogarithm? Well, because this function actually has a very nice asymptotics, where in the semi-classical limit, it goes back to the usual Dilogarithms. So here, let me summarize the properties. So it satisfies the asymptotic properties that I mentioned. So let's say if I let the parameter q to be e to the minus h, where h is a positive number, so that it is less than 1. Then if we take the limit when q goes to 1 left, or in other words, when you take h goes to 0 plus, then the function asymptotically will looks like the quantum Dilogarithm, the Dilogarithm function, like this. Or in other words, to be more precise, it says that if you take log and then you rescale by h, then this should be 1/2 negative x. Right. So it looks like the Dilogarithm under some asymptotic limits. So or after you rescale a little bit. Then it also has a very useful functional equation. And actually this, in some sense, generalizes the gamma function. So sometimes this is also called the quantum gamma function. So because for the gamma function, you have relations like this. And then you use plus. And here, taking squaring by q powers, if you use the exponential version of the variables, then this just looks like, again, the the power n, but in the q part. Yeah, some rescaling, which is I'm not going to go into, but yeah, but this sometimes is also known as the quantum gamma function. So this function is very special. It has the properties of the Dilogarithms, the gamma function, as well as the exponential function. So what does this mean? Because it is actually just the quantum exponential function, it has the quantum exponential identity. So if I let two formal variables, u and v, that Q-square commute. So these are just formal non-commutating variables. Then if I write everything as a power series, in u and v, then we have psi qv psi qu equals psi q of u plus v. So this just looks like the quantum exponential function, the usual exponential identities, right? So here we are using the power series version of your function, this one. So as a power series, you can plug in u and you can plug in v, and you can also plug in u plus v here. So then you can use the quantum binomial formula to expand your expression in terms of, say, every u will be on the left hand side and every v will be on the right hand side, or so on. And then compare both sides and see that as a power series in u and v with such an ordering, they are exactly the same. And because we are calling this the quantum dilogarithm, then we definitely expect to have a version of the pentagon identity. And the identity looks like the following. So this is again a 5-term relations, but this time written in terms of a product. But it turns out that under the semi-classical limit, so this limit, then this will becomes the pentagon for the classical dilogarithms. So indeed, this is a direct generalization of the pentagon identities. So these identities actually can be shown by combining these two functional equations. The pentagon identity can be shown by combining the two functional equations. So usually what people write is that this part will be combined to, because v q square u q square commute with v, so uv also q square commute with v. So this actually can be written as the sum by the exponential formula, while the outside terms, the green part, can actually be viewed as a conjugation of the psi qv by psi qu. And because uv q square commute with v square q, so after you conjugate, you will get such a term here. So it's something like q square u then it will becomes, so v q commute, so if you pull the v out, you will get something like this. And then this part is exactly this part here, so you will get something like v and then 1 plus q u, or q inverse u, plus or minus, I forgot. Yeah, plus. rescue you. And then you can see that this expression is exactly the expression here. Yeah, when you wrote Q VU, then it becomes Q inverse UV. Yeah, so these two will imply the pentagon identity. So here you have a conjugation. So after doing this, you can just apply Q the whole thing, and you will get the pentagon identity. All right, so to generalize the whole language to cluster mutation, remember in the classical case, we have a more general more general dilogarithm identities by writing things in terms of the tropical Y-seed mutation. So in the quantum case, we definitely expect to have similar result where we will have a version of quantum Y-seed mutation. So here definitely we are doing things involving quantum cluster algebra of some sort. So this version we will follow fock-goncharov. So the language is known as the quantum torus algebra. And we will kind of revisit this in the last lecture of the course. So here, first of all, let us consider Q to be just a formal parameter. And then everything in terms of, say, power series or so we don't care about convergence really. So as in cluster algebra, we want to have some initial seed, and we are taking the Y version. So we have initial seed B and Y. So B is just the usual exchange matrix, so there's nothing changed here. So skew symmetric, or skew symmetrizable, I think. Yeah, skew symmetrizable. Well, for simplicity, let's just take skew symmetric. Yeah. And then Y will be a collection of non-commutative variables. So two variables are non-commutative, but they definitely should satisfy something. So they will satisfy the following relation defined by the exchange matrix. So you have a bunch of non-commutative variables indexed by I, the index set of the quiver. So B will be I by I matrix. So you have such many variables, and then they will satisfy such a relation. Then we say that the quantum torus algebra, so denoted by x of B, so this will be a algebra with coefficients in rational functions in Q, generated by these variables, plus minus, subject to the relations here. So it has I generators plus or minus. So you also allow inverse of those generators, and then you will have such a Q commutation relation between the generators. So there's a more canonical way of writing such a algebra. So this involves writing the B matrix in terms of a skew symmetric bilinear form. So this will be defined on an integer lattice. Define by our matrix, so that two vectors. So first of all, it is skew symmetric. So skew symmetric, sorry, and defined by taking the matrix times transpose. Or in other words, if you have two basis vector, standard basis, then the pairing between two standard bases is just the matrix entries. So if we use this language, then equivalently we can say that the algebra will be generated by all variables of such form labeled by the integer letters and with relations given by the following equation. So it's kind of easy to see that these two definitions are equivalent to each other. So this is definitely a much more redundant set of generators because you have much more relations between them, but otherwise they are equivalent to each other. So instead of saying plus or minus, and then you say having finite product of these I and j generators, now you just consider the whole lattice spanned by them and consider all the possible relationship between those generators. So definitely we have the identification where yi above will be just the y of the standard basis below. So these two are the same thing, and these are called the quantum cluster variables. Okay, so this is the algebra generated by polynomial algebra generated by such variables. That we sometimes also will have rational expressions. So you will be dividing by some rational functions. So we probably also want to consider a bigger algebra. So let's extend things to the skew field of fraction. So we will denote by T of B to be the skew field of fraction of our quantum torus algebra. So these are just non-commutative version of the field of fractions, rational functions. So if you have non-commutative expressions, you can always write fractions of this form. So you don't write P over Q because you don't know whether it is PQ inverse or Q inverse P. Usually they are not the same. But if you just write down the order, then the nice fact about this quantum torus algebra is that it's called an OR domain, so that the skew field of fraction is well defined. So you can always write rational expressions in terms of a product of polynomials and inverse of polynomials from left to right, say. And then all the multiplications and so on will be well defined in this field. Yeah, so that really is going deep into abstract ring theory. So I'm a non-commutative ring theory. So I'm not going to do that. But let's say that the skew field fraction of the quantum torus algebra is well defined. So you can always write down rational expressions in a well defined way. All right. So let's say we have this skew field fraction. Then naturally there will be two operations that you can do on them. The first one is definitely the mutation, because you are just changing the index of the generators. So let's say if you have a mutation of the index set, then it will induce an isomorphism. On the skew field of fractions. given by sending the quantum y variables from the permuted index to the index itself. So here, yeah, sorry, this is B prime, where B prime is related to the original B by, again, this mutation. So if you have a permutation, then what you are really doing in terms of quiver is just reindexing the quiver. And then this isomorphism mu star really is just reindexing the quantum variables. So this is kind of trivial. The non-trivial one will be the mutations. So if you have a standard quiver mutation, then it will induce a homomorphism. From the field of fractions of the other back to B. So this is known as the quantum cluster mutation. And the formula is a little bit familiar, but kind of different because it's now in a quantum case. So if the index is the same as the direction of mutation k, then it's just like before, you take the inverse. Otherwise, you will have the formula of this sort. So if you just look at the right-hand side part, then if you take Q to be 1, then all these products will be the same, and you will get something like 1 plus yk to some powers, or 1 plus y inverse to some minus power. And this is exactly the tropical Y-seed mutation that we have seen. But now we have the Q factors involved, then this will be the formula that we want. So if you have a Y plus quantum cluster Y variables corresponds to the exchange matrix B prime, then this will be a homomorphism, so that these new expressions on the right hand side will still satisfy the algebra defined by B prime. Yeah, so this first write down when Q goes to 1, then this is just the usual Y-seed mutation. And also one can check that this actually is still an involution, in the sense that if you mutate the expression one more time, you will go back to the original Skew field, and then this will be the identity. So in fact, this mu k will give you an isomorphism of Skew field. All right, so this is the definition of quantum cluster mutations. And as I mentioned, the quantum dilogarithm naturally appears in the formula describing this mutation, because there's a decomposition of such a mutation into the monomial part and automorphism part. So this can be decomposed into two parts, the monomial part and automorphism part. as follows. So let's define tau k epsilon. So this will be a homomorphism of Skew field where it sends the quantum cluster variables corresponds to B prime into the tropical part or the leading term of the previous rational function. But here we take care of the signs. Yeah, so epsilon is plus or minus here. So this really is the leading term of the previous rational expression. But either we take the first or the second term, second expression. And so, for example, we may have yi times b number of yk adjusted with a appropriate factor of q. And this is precisely what this is saying. So we have yi and yk adjusted with a appropriate factor of b. And we write this instead of the usual yk so that this automatically takes care of the q factors due to this relation here, right? Because it automatically takes care of what the appropriate q factor it is, and it is the q factor that appears in front. So please just check the formula to make sure you understand and get the correct normalizations and formulas and so on. So this is the monomial part because you are just changing yi prime to monomials of y's. The automorphism part is then given by the conjugations or adjoint action of the quantum Dilogarithm functions. So this naturally is a map from TB to TB, right? Because you are taking a variable and you change it to this and then y and then the inverse of that. So everything here lies in TB, so the result is still in TB. So this is the adjoint action or the conjugation. Then the main theorem is that, the quantum cluster mutation can be decomposed into the monomial part followed by the automorphism part. So the monomial part sends TB prime to TB, right? So this is tau. And then the automorphism part sends TB to B. So it is still a map going from TB prime to TB, which is what we want. Right. TB prime to TB. So just to make sure everyone follows the notation, let's give a very simple example. Again, let's just choose our favorite two vertex quiver. So here B12, B12 is -1. So this corresponds to the Q relation, y1, y2 equals Q minus 2, Q square, y2, y1. Then the conjugation by the quantum Dilogarithm, let's say acting on y2, and let's check the action. So by definition, it's the adjoint action of phi q y1, or let me just write down explicitly the conjugation. So this is exactly what I just wrote previously, I think. So after you commute y2 with y1, you give it a q square, and then follows from the functional equation of the quantum logarithms, you will get 1 plus q y1. And this is the expression. So one can also write this as y2 plus q y2 y1, but this term is nothing but y of e1 plus e2. So let's say if you want to use the lattice version, then you get this expression, which really is just saying that the conjugation adds an extra term where the lattice is modified by another vector. So there's also a common technique of doing such calculation is to identify the quantum variables correspond to different exchange matrix with each image in the original one. And with this, we can consider all the formula inside the same Skew field. Although in this case, the mutation will no longer be homomorphisms. But this is the idea behind the fock-Goncharov cluster variety, where after we mutate, we try to, so we have two different copies of torus lying on two worlds, but they are related by mutations. And if we identify the image of yi prime with identify y prime with its image in the mutation, then what we are doing is really gluing two copies of the torus together, and by gluing such many copies, we will get what we call the cluster variety. And we will come back to this idea again in the last chapter of this course. So how do we implement such an identification? So basically, we translate all the variables in the different seed back to the original seed by the mutations. So this leads to the definition of quantum seed. Inductively, where we want to compare with the previous classical notations. So quantum seed will be a pair of the exchange matrix and the non-commutative variables. So inductively, the first one is the initial matrix and the initial y seed. I mean, it's the initial y seed. And then the t+1 one definitely will be the mutations of the t version. So yeah, here I should fix the mutation sequence. Say k1, k2, kn. A mutation sequence. So we keep mutating in this sequence and in this index. And the y seed will be the mutations, quantum mutations of the ith seed of the t+1 common torus algebra. So let me first write down the space where they live. So here, what does it mean? The B vector, the B part is clear. It's just the standard matrix mutations. So for the yi t plus 1, first of all, we want to identify everything in terms of the original quantum torus algebra. So it should be in terms of the yi sitting inside TB. So it will be some rational expression. Actually, maybe Laurent. Oh no, it's rational expression in terms of the original yi. So let's just write here. Y. Yeah, so it's just a collection of yi's. So yi will be our initial seed. So here we take the mutated matrix and define the corresponding quantum torus algebra using this matrix, and define the corresponding generators, the yi generators of this algebra. So this lies in here in TB t plus 1, and then we mutate it step by step back to the original quantum torus algebra, right? Because remember, what does this mu k do? The mu k sends the y seed at t plus 1 back to the y seed at t. So if you apply that many times, you will go back to B1. So this is well defined, and after this many application, you will get a rational expression. So it will be rational in the initial y seed. Then we can have the previous definition follows also in the quantum case. So we say that the mutation sequence is a mu period if the mutation of the exchange matrix go back to itself, and also the mutation of the y variables go back to itself. Again, everything lives in TB, in the initial quantum torus variable. And it turns out that checking whether I is mu period does not really depend on whether you are in the classical and the quantum, because the two notions actually is equivalent. So the quantum new period and the classical new period is actually the same. So if you start with a sequence of mutations that you know is a mu period in the classical case, then automatically it is also a mu period in the quantum case. So even though you add all these extra Q factors, all this non-commutative expression, the calculations is really just more complicated, but at the end, everything will go back to the original one. All right, so because of this result, we can actually write down the quantum dilogarithm identities using similar expression. Is it more or less similar expressions from previous? Actually simpler. So let's just do this theorem. So here all the results are summarized in Nakanishi's Kashaev's paper. So we first have the tropical form of the quantum dilogarithm identities. So let's start with a new period of I, and we define again the tropical sign sequence. So this will be the sign of the C vector. Of the corresponding classical y variable. So this is the same setup as the classical situation. Then the quantum dilogarithm identity is the following. In a very very neat formula. So this is it. And just a remark, all these monomials that we wrote are by definition positive monomials. Right, because the powers are all positive. Because epsilon by definition is the sign of CT. So epsilon times CT will be some positive combination of vectors. And so this is positive monomials in this sense, where you are y raising to some lattice elements where the lattice coefficient in terms of the standard basis are all positive. But of course, when you write them down in terms of the generators, then there will be some Q factors, right? For example, we have seen already, if we have such a thing, then this is positive. But of course, this equals Q y2, y1. So even though it is positive, there will be some kind of Q factors in front. So let's look at the example, and you should expect that we should get back the standard pentagon identity in, again, this case. So here again, we choose I to be 1, 2, 1, 2, 1. And then we know that the mu period, the mutation, the permutation is just interchanging 1 and 2. So let me just open a new page maybe. So if you look at the C vectors, oops, not this course. Yes, sorry. So if you look at the C vectors or our expression here, then remember the sign is just the sign of the C vector. So of the 1 to 1 to 1. So this is 1, 2, 1, 2, 1. So the sign will be plus, plus, minus, minus, minus. Then the identity will become the first one is y to the 1, 0. So it's just y1. And second one is y to the 0, 1. So it's y2. And then we have y to the minus 1. So it's 1 inverse. y1 inverse. But remember, we also have to multiply it by the sign. So y1 inverse is just y1, but you have inverse here for the sign. And then you have minus 1, minus 1. After the sign is 1, 1. So it will be y2, y1. Or y1, y2 with q in front. And I guess we have inverse. And finally, you have y to the 2. And again, inverse. And this is exactly the pentagon identity that we started with, the Q pentagon identity that we started with. So that's the basic example that everyone should start checking for rank 2 case. The proof of this, let's say just the idea, follows from the fact that by definition of mu period is the same as saying that after that many quantum mutations, you will get the mutation action. But here you can change all the mutations in terms of the monomial part and the automorphism part. So really you can write them in terms of some adjoint of quantum dilogarithms and then some monomial permutations. So after you write everything in terms of the adjoint and tau, you can rearrange the terms by pushing all the taus to the right and pushing all the adjoints to the left, and you will get some expression like this. But tau are really just monomials, so you can check that the action of this tau, all the monomial action on the variables will be the same as the permutations that we have, which means that the adjoint action has to be the identity, and then you will get that. So this is the left hand side, and you will get that the left hand side of, because the adjoint is identity, and one can argue that there's nothing commute with all the variables, so the thing that you conjugate has to be identity also. And so let me just write that down here. Yeah, so please just look at the paper for more details. So this is the tropical form, and one can try to play around with this relation by pushing again the y's to the other side, for example, and then we will arrive at the universal form, which is less common, and the argument will involve rational expressions. So this is the rational form. So remember, these are all rational expressions of the original TB quantum torus algebra in terms of the y1 up to, in terms of the yi of the original TB algebra. And the proof basically follows from the shuffle formula, that if you have the following expression, so this is the expression on the left of the left hand side of the tropical form, then one shows that this is the same as this by induction. So by induction, one can show that these two are the same, and in particular, the universal form is just the case when t is n, the last case. So when t is n, then the left hand side is 1 by the tropical form identity, so the right hand side is also 1. So as an example, the previous identity can be written as follows. Yes, so this is the formula. I hope it is correct. Anyway, so all right, so here I will want to mention the fact again that the maximal green sequence gives you mu period. So by this result, we will have all different quantum Dilogarithm identities coming from maximal green sequence. So this is the idea behind the combinatorial Donaldson-Thomas invariant of a quiver, introduced by Keller. So we introduce EI to be the product of the left-hand side. Then the claim is that if I and I prime are any pair of maximal green sequence, then this expression does not depend on the choice of I. And this is known as the redefined combinatorial Donaldson-Thomas invariant of your quiver Q. So in the special case, or I mean, not special case, but we all know that if you have two such a maximal green sequence, then this will be a period because it is a frozen isomorphism. And the above formula basically just turned it into the tropical form of the quantum Dilogarithm identity. Right, so Donaldson-Thomas invariant is something that is useful, introduced by Conserfish, I think, in algebraic geometry, and this is a kind of a combinatorial version of that. So you can also see the reference by Keller in his survey for more discussion on this fact. So the final fact about this quantum Dilogarithm identity is that if your quiver is the thinking diagram with alternating arrows, then remember we have two green sequence. One is given by I plus I minus, and the other is given by I minus I plus, but H times, where H is the Coset number. Then the fact is that this identity is actually a consequence of the pentagon identity. So even though you have many terms here, you can actually derive these identities from just all the 5-term relations. So you keep applying the pentagon, and you will get such an identity. So this is the meaning that in this special case, there's nothing new here. Basically, it says that everything is just pentagon identity. All right, so in the last part of today's lecture, I also want to introduce the non-compact version that I promised in the beginning. So the idea is that we assumed that Q is less than 1 when we define this infinite product expression or the power series expression. But if we take the modulus of Q goes to 1, then this is not well defined. They diverge. But it turns out that there's a remedy for that. And this is introduced by a meromorphic function, so that the compact version, the one with less than one, q less than one, is actually, if the non-compact version is actually a ratio of the compact version for different parameter q, and after you take the limit, you will tend to the correct function. So let's stick to this situation, and we let e q to be e to the pi I b squared, and we are interested in the case when b is real. But first, let's relax a little bit and say b is a complex with non-zero real part. And we also introduce the following notation, q tilde. So this will be b inverse. And finally, we introduce this constant. Then the non-compact quantum dilogarithm is the following. So I use phi of b. So this is exponential of such an expression. So this is the formula where sine h is the hypersine function. And this is actually a contour integral where the contour goes over the pole at 0. So if t0, and then your contour will have a small semicircle going through t equals 0. And when checked that this integration will converge in the range when the imaginary part of C is less than imaginary part of CB. So this is the expression for this region, and it can be analytic, continued to a meromorphic function in C. So with poles and zeros. Yeah, so we are actually interested in the case when B is real. So in that case, we actually have a nice graph for that. So I forgot what value of B is, but yeah, let's say this maybe 0.7, I think. So this is the graph kind of for the quantum dilogarithm function. So what is the meaning of this graph? So this is one way to draw complex functions on a complex plane. So the color will represent the phase of your complex numbers, so the argument, the angle of your complex number, while the brightness and darkness represents the magnitude of your complex number. So you can see that in this graph, the function, so this is the function phi bc. So you can see that when your, so this is real, I think this is the real line. Let me just draw. So this is the real line. And I think this is the axis. So you can see that this function, when c goes to negative infinity, then it becomes a pure purple color. So it will asymptotically becomes a constant, while it is exponentially increasing in size on the upper quadrant and decrease to 0 in the lower quadrant. So here maybe you're not easy to see, but you can see that all these white dots will be the poles, and all this black dot will be the zeros of your meromorphic functions. And finally, on the axis of symmetry, so here, when C is real, it turns out that the modulus is actually just 1. When C is real. So it's somewhere in between black and white. Yeah, I should draw back the axis. So this is the graph. So let's just write down several properties of this function. So first of all, as I mentioned, this is a non-compact version, so it has to relate to the original compact diagram function. And the statement is the following. So if you have if your parameter b has positive imaginary part, so that by definition these two are less than 1. So remember, Q tutor is e to the pi I b inverse. This is e to the pi I b square. Then your function defined above is given by the ratio of two quantum diagram functions. So this sometimes is known as the modular double, again introduced by Fadiev, because you can see there's like a duality between B and B inverse in this formula. So this says that even though each compact diagram function will diverge when Q goes to 1, but if you take the ratio of two such compact diagram function and you take Q goes to 1, it will converge to a meromorphic function where B can be taken to be a real parameter. So this is the way that the Q limit when Q goes to 1, and the modulus of Q goes to 1 can be treated using a separate, different complex meromorphic function. And this function also enjoys, sorry, this is fine. And this function also enjoys all this modular double duality I mentioned here. So one can see quite easily from the definition that the expression is independent of whether you choose B or B inverse. And it also satisfies the version of the of the gamma function, something like the gamma function, as I mentioned before. I mean, if you change your C rescale to the complex axis and do some rescaling, it looks like the gamma function, but there's more because it is actually doubly periodic because of the B and B inverse duality. So this is why it's called the double gamma function, and this function actually in a different form is introduced by Barnes in 1901, which is very old. And finally, we also have the asymptotic formula. In terms of the Dilogarithm function. Right. And then and finally, also, if B is real, or the modulus of B is 1, then this function has norm 1 for real C. And this is very useful, at least for my purpose, because by functional calculus, in functional analysis, if you have a self-adjoint operator on a Hilbert space, then automatically this expression will be a unitary operator on X. And so this is the main reason why this is useful in the study of cluster varieties or the its representation, because now you have a quantum dilogarithm where you can insert all these quantum cluster variables, and with the associated positive meaning, just like before, the powers of the y is positive, then they are self-adjoint, and you can plug it in to this phi, and then you will obtain unitary transformation of Hilbert space, and that will provide us many intertwining operator giving unitary equivalence between different representations. So this is kind of a remark. So if you're not familiar, it's fine, I think. Yeah, so self-adjoint is the usual meaning of self-adjoint, right? Okay. All right, so finally, we can also bring in the pentagon identity from the compact case to the non-compact case using precisely this ratio formula. And it translates to the following statement. So let's say we have P and Q are the position and momentum operator. So precisely, I mean, this means that the commutator between them is 1 over 2 pi I. So these are operators where PQ minus QP is 1 over 2 pi I. A usual choice will be multiplication by X and differentiation by X. So if you have two such operators acting on, say, L to R, so this will be self-adjoint operators. Then you can plug into the quantum dilogarithm. And as mentioned, these are self-adjoint, so that these are all unitary operators. So they are well defined. And the statement says that as unitary operator on your Hilbert space, the following identity holds as unitary operators. Right. And it turns out that it is this classical limit of this using what's called the saddle point method, say in Nakanishi's paper, will produce the pentagon for the dilogarithm functions. Oh, let's say for L, yeah. So the idea basically is that because you have operators on Hilbert space, and then this is a unitary operator, you can actually rewrite in terms of the previous explicit formula that this operator can be represented by integral operators. So something like this. Yeah, so say Rn. So let's say if your Hilbert space is Rn, L to Rn, then an operator acting on a function is called integral operator if it can be written in this way, where this is just a normal usual function, not a operator, but just a usual function, and you integrate. So this again is the quantum dilogarithm functions, but in two variables. And this is in terms of an operator. So the left-hand side this is a operator, while this is just a function, and this is operator. So you write your operator in terms of integrating over a function, and then you do the settle point method, where basically you find the critical point of such an integrand and solve for the maximum minimum. And then the settle point method tells you that at the classical limit, so all the deformation, the Q deformation part will be cancelled. So the maximum will occur when it only has the leading term, which corresponds to the classical limit. Something like that. So I didn't check the details. So if you're interested, you can consult the paper. So here, the final thing I want to mention about the non-compact dilogarithm is that, so we have the pentagon. So we definitely want to have the general version in terms of the mu period. And this will become the local form. So intuitively, it really is saying that these P and Qs are not the y before, but the log of y before. So we will want to introduce the exponential of those variables. So let us stick to the case when b is real. And I let d to be the operator given by the following expression. So here I really have I copies of the position and momentum operator, where the j and k copy do not commute if they are not having the same index. So I just generalized the previous rank 1 case to higher rank, and I let d to be this expression. Then I define the y variable to be the exponential of this d, and the c variable to be the modular double version. So just remind, these are unbounded operators. Then first of all, we have the following proposition. So algebraically, they satisfy the same Q commutative relations that we want. Oops. And they commute otherwise. So Y and Z are commuting copies of the quantum torus algebra corresponding to Q and Q tilde respectively. And so this all holds on some dense domain of your Hilbert space. So one good choice will be those of the form e to the minus square times some polynomials in terms of x. So polynomials of this form, then these operators will act on this dense subspace and satisfies these commutation relations. And finally, we have the local form, which really is just taking log of the previous tropical form. So if we have a mu period, then you have such a relation. where I denote D by the D hat vector. So D vector is a collection of D1 to Dn, and so this is just a standard vector space dot product. So with this dot product, you will get a combinations of P and X, and you raise to the exponential, you will get back Y. So this really is just the previous tropical form identities, but you kind of take log and represent it in terms of the phi function. So one should be easily see that this follows from the fact that phi b is really just the ratio of 2 psi q in the corresponding in the limit when b is not real. In the case when b is not real. Right. So yeah. So this is a very rough introduction to the quantum dilogarithm functions. So if you will be doing research in this direction, then you are welcome to discuss more with me on this part. Otherwise, starting from next class, we will talk about a new topic, which is the cluster algebra arising from surface, and we will discuss how the triangulation of surface corresponds to the cluster algebra data, and how one can remedy the case when you cannot do mutations to get a full correspondence between the cluster complex. And if time permits after that, then we will talk about the generalization of this cluster algebra from surface, which is known as the higher type vector theory. And we will introduce fock-goncharov language. And at that time, we'll again come back to this language of quantum torus algebra and all this stuff that may appear there. All right, so this class is a long lecture, so thank you for your patience, and we will see you next time.